Hello everyone and welcome to this session on 8086 instruction set. This session is a part of Module 2 of the course CS305 Microprocessors and Microcontrollers for the 5th semester BTech Computer Science and Engineering students under the APJ Abdul Kalam Technological University. Myself Anu Maria Joykuti from the Department of CSE, Rajagiri School of Engineering and Technology. The 8086 instruction set can be broadly classified into the following types of instructions, which are the data copy or transfer instructions, the arithmetic instructions, the logical instructions, the string instructions, branch instructions, flag manipulation instructions, and machine control instructions. The data copy or transfer instructions. This type of instructions are used to transfer data from the source operand to the destination operand. All the store, move, load, exchange, input and output instructions belong to this category. We'll be seeing in detail about the various data copy transfer instructions in the coming slides. First is the move instruction, which is used for data transfer or copy. The move instruction copies data from a specified source to a specified destination. The format of this instruction is as given here, that is move destination comma source, where the destination can be a register or a memory location and the source can be a register, a memory location or an immediate data. The source and the destination cannot both be memory locations. The examples of the move instruction are given here, which are move AX, 5000H, where the immediate data 5000H will be moved to the AX register. Another example is move AX, BX, where the data that is present in the BX register will be moved to the AX. Move AX, SI, where the data that is present in the source, the data that is pointed by the source index register, SI register, will be moved to AX. Another example is move AX, 2000H, which is the direct addressing mode. So the data that is present in the address location 2000H will be moved to the register AX. Next we have the push and the pop instructions. The push instruction is used to push the contents of a specified register or memory location in the instruction onto the stack. This push instruction decrements the stack pointer by 2. The format of the instruction is as given here, that is push source. The source can be a general purpose register, a memory location or an immediate number. The examples of the push instruction is as given here, which is push BX. Here what happens is that the contents of BX register will be pushed onto the stack. Next is push DS. The contents of the DS register data segment will be pushed onto the stack. Next is push 5000H, which is the direct addressing mode, and here the contents of the memory location 5000H will be pushed onto the stack. Next we have the pop instructions, which is used for copying from the stack location that is pointed by the stack pointer to the destination that is specified in the instruction. Here the stack pointer will be incremented by a factor of 2. The format of the instruction is pop destination, and the destination can be a general purpose register, a segment register or a memory location. The examples of the pop instruction is as given here, that is pop BX, where the content of the stack, which is pointed by the stack pointer, will be copied to the BX register. Pop DS, again the content of the stack will be copied onto DS. Next is pop 5000H, where the contents of the stack will be copied to 5000H, the memory location 5000H and 5001H. The XCHG instruction or the exchange instruction. This instruction is used for exchanging the content of a register with the content of another register, or it can be exchanged with the content of a memory location. The XCHG instruction format is as given here, which is XCHG destination comma source. However, the XCHG instruction cannot be used for directly exchanging the contents of two memory locations. Here are few examples of the XCHG instruction, which the first one is XCHG AX, BX, where the contents of the registers AX and BX are interchanged. Another example is XCHG 5000H, AX, where the content of the AX register is being exchanged with the content of the memory location 5000H. Next we have the XLAT instruction or the translate instruction. This instruction is used for finding out the codes in case of a code conversion problems, and this is done by making use of lookup tables. So suppose we have to translate a byte from one code to another code, that is from a source code to a destination code. In that case we can make use of the XLAT instruction. Now the byte or the code, the byte that is present in the source code has to be loaded into AL, and there has to be a lookup table which will have all the set of codes in the destination format. So this lookup table has to be loaded into the data segment, and then BX will have the offset of that address in DS. Now when the XLAT instruction is being executed, there is a translation that is being happening where the code that is present in AL will be added to the content of BX, and the final result is getting stored in AL again. We'll explain this with the help of an example. The first instruction is move AX comma segment table, where the address of the segment containing the lookup table is being moved to AX. Next, move DS comma AX. So the content of AX, that is the offset of the segment table, is now present in the data segment. Next, we have the instruction move AL comma code, where the code of the byte that needs to be translated is now present in AL. That is, the byte that needs to be translated is now present in AL. Next, we have the instruction move BX comma offset table, which will move the offset of the code lookup table into BX. Next, the XLAT instruction is being executed. When the XLAT instruction is being executed, the content of BX and AL gets added up, and this result is stored in AL by replacing the code that was present before the execution of the XLAT instruction. So now we have the translated code of AL present in AL again. The in instruction, which means input the port. This instruction is used for reading an input port. The input port address, or the address of the port which has to be read, may be specified in two ways, which can be either specified directly or indirectly. The format of this instruction is in accumulator comma port. Here the AL and the AX are the only registers that are allowed as destinations for the 8-bit and the 16-bit operations respectively. And DX is the only register which is allowed to carry the port address in the implicit mode. We'll explain this with the help of two examples. First example is in AL, 0300H. Here what happens is that the instruction will read the data from an 8-bit port whose address is given in 0300H, and it will read the contents from this particular port, and it will store it in AL. Next, we have the instruction in AX. Here what happens is that the address of the 16-bit port will be present in the implicit manner in the DX register. So it will read the contents, it will read from this input port whose address is given in the DX register, and it will store it in the AX register. Next, we have the out instruction, which is used for output to the port. Here what happens is that this instruction is used for writing to an output port. So the port address can be again specified in two ways, directly, or it can be implicitly given in DX. The format of this instruction is out port comma accumulator, and again AL and the AX are the only sources that can be used respectively for the 8-bit and the 16-bit operations, and DX is the only register which will carry the port address in the implicit mode of operation. We'll see two examples for the out instruction. The first one is out 0300H comma AL. Here what happens is that what this instruction does is that it will send the data that is available in the AL to the port address that is specified in 0300H. Next instruction is out AX. Here the address of the port is given in an implicit manner in the DX register. So what this instruction does is that it will send the data that is available in AX to the address location that is specified implicitly in the DX register. The LEA instruction, or the load effective address instruction. This instruction loads the offset of an operand into a specified register. The format of this instruction is LEA register comma source. We'll see this, we'll explain this with the help of an example. So if the instruction is LEA BX comma ADR, what this instruction does is that it will load the offset of the label ADR into the BX register. Now this instruction is more useful for assembly language rather than for machine language. Next, we have the LDS or the LES instruction, which means load pointer to DS or ES. What this instruction does is that it will load the DS or ES register as it is differentiated by LDS or LDS, and it will load the DS or ES register and also the specified destination register in the instruction with the content of the memory location as specified as source in the instruction. For example, if the instruction format is LDS register comma source, or it can be LES register comma source. We'll see an example. So the first example is LDS BX comma 5000H. Here what happens is that the source is 5000H and the destination register is BX. So what this instruction does is that it will load the content of the memory location 5000H into the BX register, and also it will load it into the DS. Similarly, if the instruction is LES BX, 5000H, then it will load the content of the memory location 5000H into the BX register and also into ES. The LHF instruction, or load AH register from the lower byte of the flag. What this instruction does is that it will load the AH register with the lower byte of the flag register. Next is the SAHF instruction, which is store AH to lower byte of the flag register. Here what happens is that it will set the condition code flags in the lower byte of the flag register. It will set or reset the condition code flags in the lower byte of the flag register with the byte that is present in the AH register. Next is the pushF instruction, which means push flags to stack. Here what happens is that it pushes the flag register onto the stack. First, the upper byte of the flag register is being pushed, and then the lower byte is being pushed onto the stack. The stack pointer is decremented by 2 for each of the push operations. Next is the popf operation, which means pop flags from stack. Here what happens is that it will load the flag register, that is both bytes of the flag register is being loaded by the contents of the memory location that are currently pointed by the stack segment and the stack pointer. The stack pointer is incremented by a value of 2 for each pop operation. The next category of 8086 instructions are the arithmetic instructions. These instructions usually perform the arithmetic operations such as addition, subtraction, multiplication and division. The increment and the decrement operations are also belonging to this category. The arithmetic instructions affect all the condition code flags. The operands can be either the register or memory locations, or it can be immediate data depending upon the addressing mode. We'll be seeing about each of these arithmetic instructions in detail in the coming slides. The first instruction in the category of arithmetic instruction is the add instruction, which performs the addition operation. So this operation adds data from the source to the data in the destination, and the result of the addition operation will be stored in the destination itself. The format of this instruction is add destination comma source, where the destination is the can be a register or a memory location, and the source can be a register, a memory location or an immediate number. However, the source and destination cannot both be memory locations. The example of the add instruction is as given here. The first example is add AX, 0100H, which is the immediate addressing mode. Here, the immediate number 0100H will be added onto the contents that is present in the AX register, and the result will be stored in the AX register. Next instruction is add AX, BX, where the contents of BX will be added to the contents of AX, and the result will be stored in the AX register itself. This is an example of the register addressing mode. Next is add AX, SI, which is the index addressing mode. So here the offset address that is present in the SI register will point to a data, and that data will be getting added to the contents of AX register, and the result will be stored in AX. Next is add AX, 5000H, where the contents of the memory location 5000H will be added on to the contents in AX, and the result will be stored in AX. This is an example of the direct addressing mode. Next example is add 5000H, 0100H, where the immediate number 0100H is getting added to the contents of the memory location 5000H, and the result will be stored in the memory location 5000H itself. Next is add 0100H, which is the implicit addressing mode, where 0100H, the immediate number 0100H, is getting added to the contents that is present in AX, which is specified implicitly, and then the result will be stored in the AX register itself. The next is the add with carry instruction, which is specified as ADC. This operation is same as that of the add instruction, but it also adds the carry bit flag to the result. The carry bit flag, which may be set as a result of the previous calculations, is also being added to the result in this case. All the condition code flags are affected by this instruction. The format of this instruction is ADC destination, source. And the destination and source are the same as in the case of the add instruction. The examples of the ADC instruction is ADC 0100H, where this is the implicit mode where the AX is the implicit operand here. So here what happens is that the immediate number 0100H is being added to the contents of AX along with the value that is present in the carry flag. Next is ADC AX, BX, where the contents of AX and BX are getting added, and the carry flag is also, carry bit is also being added to the result. Next is ADC AX, SI, which is the index addressing mode. So here the data that is present in the offset that is present in SI will be added to the contents of AX with the carry bit. Next is ADC AX, 5000H, which is which is the direct addressing mode, where the contents of the memory location 5000H is getting added to the contents of AX along with the carry bit. Next is ADC 5000H, 0100H, where the immediate number 0100H is getting added to the contents of the memory location 5000H along with the carry bit. Here, just like add operation, the result will be stored in the destination itself. Next is the compare instruction, which is specified as CMP. So the compare instruction, what it does is that it compares the source operand with the destination operand. The format of this instruction is CMP destination, source. The destination can be a register or a memory location, and the source can be a register, a memory location, or an immediate number. So in order to perform the comparison, this instruction subtracts the source operand from the destination operand, but the result is not getting stored anywhere. The flags will be affected depending upon the result of the subtraction. For example, if both the operands are equal, then the 0 flag will be set. If the source operand is greater than the destination operand, then the carry flag will be set. Or if the destination otherwise the carry flag will be reset. The example of this instruction is as given here, which is CMP BX, 0100H, where the immediate number 0100H is getting compared to the result, compared to the value that is present in the BX register. Next is CMP 0100H, where the immediate number 0100H is getting compared to the data that is present in the AX register. This is implicitly specified, and the flags will be set accordingly. Next is CMP BX, CX, which is the register addressing mode, where the contents of the CX and the BX register are getting compared. The increment and the decrement instructions. The increment instruction, which is specified by INC. This increments the contents of the specified register or memory location by 1. Here all the condition code flags except the carry flag are getting affected by this instruction. The format of this instruction is INC destination. So the operand, whatever is the content of the operand, here a value of 1 is getting added to it. The example of the INC instruction is INC AX, where the data that is present in the AX register is incremented by a value of 1. Next is INC BX, which is the register indirect addressing mode. So here the data that is present at the offset specified by the BX register will be incremented by a value of 1. Next is INC 5000H, which is the direct addressing mode. Here the data that is present in the memory location 5000H is getting incremented by 1. Next is the decrement operation, which is specified as DEC. Here a value of 1 is getting subtracted from the contents of the specified register or memory location. Here also all the condition code flags except the carry flag are getting affected. The format of this instruction is DEC destination. The example of this instruction is DEC AX, where the contents of the AX register is getting decremented by a value of 1. Next is DEC BX, which is the register indirect addressing mode, where the contents of the offset address that is present in the BX register is decremented by a value of 1. Next is DC 5000H, which is the direct addressing mode. Here the contents of the memory location 5000H is getting decremented by a value of 1. The subtract instruction, which is given as SUB. The subtract instruction subtracts the source from the destination, and the result of the operation will be stored in the destination itself. The format of this instruction is sub destination, source, where the destination can be a register or a memory location. The source can be a register, a memory location, or an immediate number. The source and the destination cannot both be memory locations together at the same time. So the example for the subtract operation is SUB 0100H, which is the Immediate addressing mode. So here the destination is implicitly specified as AX. So here what happens is that the immediate number 0100H is being subtracted from the contents of the AX register and the result is being stored in AX itself. Next is SUB AX, BX, which is the register addressing mode. So here the contents of BX is getting subtracted from AX and the result is stored in the AX register. Next is SUB AX, 5000H, which is the direct addressing mode. So here the contents of the memory location 5000H is getting subtracted from the contents of the AX register and the result is getting stored in AX. Next is SUB 5000H, 0100H, where the immediate number 0100H is getting subtracted from the contents of the memory location 5000H and the result is stored in 5000H itself. Next is the subtract with borrow instruction, which is specified as SBB. Here what happens is that it subtracts the source as well as the borrow flag, which is the carry flag, from the destination and the result of this operation is getting stored in the destination. The borrow flag may be set as a result of a previous calculation. So what it does is that the subtraction with borrow means subtracting 1 from the subtraction obtained by SUB if carry or borrow flag is getting set. That is, it is same as subtract operation, that is SUB operation, but apart from that it also subtracts a value of 1 from the result if the carry flag is being set. The format of this instruction is SBB destination, source, where the destination is can be a register or a memory location and the source can be a register, a memory location or an immediate number. The source and the destination cannot both be memory locations. So the examples of this SBB instruction is given here, which is SBB 0100H. What happens here is that it will subtract the immediate number 0100H from the AX contents of the AX register, which is implicitly specified, and it will also from that result it will also subtract a value of 1 if the carry flag is being set, and the result of this instruction is being stored in the AX register. Next is SBB AX, BX, where the contents of BX is being subtracted from AX, and in addition to that a value of 1 will also be subtracted, which depending on the value of the carry flag, and the resulting final result will be stored in AX register. Next is SBB AX, 5000H, where the contents of the memory location 5000H is getting subtracted from the contents of AX, and depending on the value of SBB, value of the carry flag, 1 will be subtracted from this result and the final result will be stored in the AX register. Next is SBB 5000H, 0100H, where the immediate number 0100H is getting subtracted from the content that is present in the memory location 5000H, and along with that a value of 1 will be subtracted depending on the value of the carry flag, and the final result will be stored in the 5000H memory location. Next is the multiplication operations, which are specified by the instructions MUL and IMUL. The MUL stands for unsigned multiplication byte or word. What the MUL instruction does is that it multiplies an unsigned byte or a word by the contents of AL or AX register. The format of this instruction is MUL source, where the source can be a register or a memory location. The result will be stored as follows. The most significant word will be stored in the DX register and the least significant word will be stored in the AX register. Here no immediate operands are allowed. The example of the MUL instruction is as given here. The first example is MUL BH. Here what happens is that the contents of the BH register is getting multiplied by the contents of the AL register, and the result will be stored in the AX register. The second example is MUL CX, where the contents of the CX register is getting multiplied with the contents of the AX register, and for the result the least significant word will be stored in the AX and the most significant word will be stored in DX. Next is the IMUL instruction, where what happens is that it multiplies a signed byte or a word by the contents of AL or AX. The signed byte or a word will be present in the operand that is given in the instruction. The format of this instruction is IMUL source, where the source can be a register or a memory location, and the result will be stored in the same way as that of the MUL instruction, where the most significant word is in DX and the least significant word is in AX. Here also no immediate operands are allowed. The example of the IMUL instruction is as given here, where IMUL BH means that the content of the BX register is getting multiplied with the content of AL and the result is stored in AX. Next is IMUL CX, where the content of CX and AX is getting multiplied and the resulting the result is getting stored in such a way that the LSW or the least significant word is in the AX and the MSW or the most significant word is in the DX register. The next instruction is for the division operation, which is specified as DIV, which is for the unsigned division operation. Here this instruction divides an unsigned word or a double word by a 8-bit or a 16-bit operand. The format of this instruction is DIV source. In the case of a 16-bit operation, the dividend will be present in the AX register. The divisor will be specified using any of the addressing mode except immediate addressing mode. The quotient of this division operation will be present in the AL register and the remainder will be present in the AH register. In the case of a 32-bit operation, the dividend will be a double word of which the least significant word or the least significant 16-bit will be present in the AX register and the highest significant word will be present in the DX register. The divisor can be specified using any of the addressing mode except the immediate value, and the quotient will be present in the AX register and the remainder of this division operation will be present in the DX register. This division instruction does not affect any flag. The example of the division instruction is as given here. The first example is DIV BL, which is a 16-bit operation. In this case, the dividend will be present in AX. The divisor is in the BL register. So after this instruction is being executed, the quotient will be present in the AL register and the remainder will be in the AH register. Next is the example for a 32-bit operation, which is given as div CX, where the dividend, the LSW of the dividend will be present in AX, the HSW will be in DX, and the divisor is there in the CX register. So after execution of this instruction, the quotient will be there in the AX register and the remainder will be there in the DX register. Next is the IDIV instruction, which is the signed division operation. This is same as the DIV or the division instruction, but with signed operands. The format of this instruction is IDIV source. So same as in the case of unsigned division, here also we have 16-bit operation and 32-bit operation. In the case of a 16-bit operation, the dividend will be in the AX register and the divisor can be specified using any of the addressing modes except the immediate addressing mode, that is no immediate operand is allowed here. The quotient of the division operation will be present in the AL register and the remainder will be in AH. Next is the 32-bit operation, where the dividend is a 32-bit double word, where the LSW is present in AX, the HSW will be in DX. The divisor will be specified using any of the addressing mode except it cannot be an immediate number. The quotient will be in AX and the remainder will be in DX in this case. The result will be a signed number and all the flags will be undefined after the execution of this particular instruction. A divide by zero interrupt is generated if the result is too big to fit in the AX register in the case of a 16-bit operation, or if it's too big to fit into the AX and the DX register in the case of a 32-bit operation. The example of this instruction is given here. The first example is IDIVBL, where the contents of the AX register is getting divided by the contents of the BL register and the resulting quotient will be present in AL and the remainder in AH. Next is IDIVCX, which is a 32-bit operation. So here the divisor is in CX, the dividend will be in AX and DX, that is LSW in AX, HSW in DX, and after the execution of the instruction, the quotient will be present in AX and the remainder will be in DX. The CBW instruction, which is to convert a signed byte to a word. This instruction converts a signed byte to a signed word. In other words, it copies the sign bit of a byte to be converted, which is present in AL, to all the bits in the AH register. The result of this operation will be present in the AX register. This instruction will not affect any of the flags. Next is the CWD instruction, which is to convert a signed word to a double word. Here what this instruction does is that it copies the sign bit of a word which is present in AX to all the bits that is in DX. This instruction is being performed before the sign division. This instruction also does not affect any of the flags. Next is the negate instruction, which is given by NEG. This instruction replaces the number in a destination with its 2's complement. The destination can be a register or a memory location. The format of this instruction is NEG destination. This affects all the condition code flags. The example of this instruction is NEG AL, or it can be NEG BX. These are two of the examples. And that's all that we have in this session. The remaining part of the instruction set will be covered in the following sessions. Thank you.